All right. Well, welcome everyone to the latest in our Lunchtime seminar series. Our speaker today, John Hargreaves, probably needs little introduction for many of you, but I'm going to introduce him anyway. John Hargreaves was awarded an MEng in Engineering and Computing from Computing Science from the University of Oxford and a PhD in Acoustic Engineering right here in Salford in 2007, where he remains a lecturer in Acoustic and Audio Engineering. He's known for his research on novel computational acoustic algorithms, notably boundary integral methods. Tongue twister. But he also has strong research interests in loudspeaker design and characterization, material characterization, and microphone arrays. He's a member of the IOA Research Coordination Committee and the UK Acoustics Network Special Interest Group for Computational Acoustics, and since 2020 has had the pleasure of consulting for RA Aerospace on their direct field acoustic testing requirements. John has had the pleasure of being involved in a wide variety of public engagement activities, including several TV appearances, and is passionate about performing, engineering, and enjoying live music. He was awarded the UK Institute of Acoustics Tyndall Medal for outstanding contribution to acoustics research and education in September 2016, and is here to talk to us today about founding the Acoustic Centre of Loudspeakers. So without further ado, I will hand over to John.
Thank you, everyone. Hello, just a further reminder to those online, see a few more join. If you get your cameras on, you'll get recorded and put on YouTube, so while it's nice to see your faces, you might wish to turn them on. Oh, hi, Paul. I'm not going to keep saying that over and over again. You're going to get recorded if you've got your cameras on. Right, so hopefully you can all see my screen okay. Please let me know if not. I might just mute the computer though, because there's constant binging whenever anybody joins the meetings. Quite distracting. So, so this is a talk I gave in the Reproduce Sound Conference in Bristol back in November, and I just thought it'd be nice to come here and do it again, because it was one of those things that started off as probably a small idea, then ended up sort of growing and evolving into a rather more substantial piece of work than I frankly intended. So, in fact, to be honest with you, I'd meant to present this in 2022, and actually it got so out of hand I had to delay it a whole year before I actually got around to finishing it. So such is the life. So, quick outline first of all. I'm going to talk a bit about what the Acoustic Centre concept is, a bit of motivation, a bit of history. I'm going to talk about how it relates to something called spherical harmonics, which some of you have met before. If not, then I'm going to tell you about them. I'm going to show some results for the Acoustic Centre for some analytical sources, so not actual. I'm thinking mostly about loudspeakers, as you might have sort of gathered from the, if you've seen the image for this talk, but just start off with some sort of theoretical, mathematical descriptions of sources and see if we can find them. And then we're going to move this on to a single driver loudspeaker, and then actually these two things are in the wrong order. We'll talk about optimisation of cardioid loudspeaker, and I'll also, hopefully if there's time, talk about, let's reset that timer, talk about a loudspeaker in or above an infinite baffle as well, which wasn't in the Reproduce Sound talk, but I, in my classic style, had made more slides than I had time to present, so luckily you come along here, I've already got a talk that's too long. So, here we are. So, Acoustic Centre, a bit about motivation and history. Hello, come on in. So, what is the Acoustic Centre? Well, you'll see some definitions in words if you look in different standards, and you might find such as the fact that it's the position from which sound pressure varies inversely with distance. That might be one way. Someone tries to say, where is this centre that the sound is coming from a certain source? Or they might also say something like it's a point from which spherical wavefronts appear to diverge. So there's kind of two different definitions there, one based on sort of how pressure decays with distance, one on to do with kind of wavefront shape, and therefore perhaps maybe a little bit to do with phase. And these are really pretty simple, but actually as you get into it, as you dig into it, as I did, and say the whole thing fell back by a year, quite nuanced in practice once you actually get into the detail. So we'll see some of that later on. So what is the Low Frequency Acoustic Centre for Loudspeakers? Well, this kind of the interest in this area really stems from an Audio Engineering Society conference paper by John van der Kooi, which was back in 2006. And actually that presents some quite sophisticated theory and an axisymmetric boundary element method model, actually, which is a bit like what you're going to see some of today. And there was quite a lot of, say, quite sophisticated theory there, but really what people seem to remember mostly is the more practical method that's illustrated by this diagram, this sketch here out of the paper. And if you're going to follow this, the principle of position from which sound varies inversely with distance, if that's how you think the acoustic centre is defined, then essentially what this is doing is it's comparing the sound pressure level at the front and the back, and then by doing a bit of a calculation, working out in a closed form way. So it's just an equation. You put those two SBLs in, and it'll tell you where the acoustic centre is based on this quite simple calculation. And that has the benefit of simplicity, and has the benefit that it's just a closed form thing. Two sound pressure level measurements, out comes the answer. Parallel to that, and actually going on a little bit longer, there was a whole other area of study which is Acoustic Centre for measurement microphones, which I've heard various people here talking about as well, since actually now we've got the designated institute status in the UK and there's more microphone calibration stuff going on. Some notable references from that are Trott in 1977, the year I was born, and also Finn Jakobsen and all in 2004, which both discuss acoustic centres. If it's a concept that's been around for quite a while, I can't say that I dug all the way back to find the first possible mention of the word, but it's kind of obvious that this is the general idea has been around for a while. Van der Kooi actually stated in 2010 that he was unaware of this whole body of literature when he kind of coined the term for loudspeakers in 2006. Well, this is a very similar concept as it will be for loudspeakers, but of course it's for sensors instead of sources. So you're thinking where, do we imagine the sound kind of coalescing onto this microphone? So there's kind of reciprocity principle there. And obviously it applies to higher frequencies due to the smaller size, because it's the ratio of size to wavelength that drives the physics we're thinking of here. As with Van der Koi's acoustic centre definition, this is limited to omnidirectional transducers. So I guess that makes sense with Van der Kooi. He was thinking about closed box subwoofers that are pretty much omnidirectional. Measurement mics are usually designed to be omnidirectional, so that also makes sense. But really, these days, obviously we see a lot of microphones that are not omnidirectional. We see now start to see a lot of loudspeakers, like cardioid subwoofers, that are not omnidirectional, and that kind of opens up some questions of what you might do next. But the omnidirectional statements for omnidirectional transducers are still really useful, and this and Van der Koi's approach has been brought together really nicely in a 2023 JASA paper by Sam Bellows, who actually saw during the Teams meeting a minute ago. It's very nice. Hi, Sam. And Tim Leishman, who are both at Penn State. And yeah, they brought those together, and that kind of was a bit of serendipity, I felt, really, because I delayed this this paper by a year, this conference paper, and in the meantime, these guys wrote a nice JASA paper and did some of my work for me, so that was fantastic. In line with this, there's also a concept of high frequency acoustic centre for loudspeakers, and this is a little bit different. So this is kind of synonymous with the kind of loudspeaker measurements I've drawn shown on the bottom right here. And here the cabinet's now large with respect to wavelength, so features like cone size, baffle size, edge diffraction, horns can achieve significant pattern control. And really what people are thinking about then is it's the origin for when they're doing loudspeaker balloon measurements. So here's a speaker that actually belongs to me, incidentally, on our ELF robot in our anechoic chamber doing some measurements. And usually what you do, I've got a sensor in the near field there, but usually what you do is get as far away as possible, have a microphone, and then rotating the speakers, equivalent to rotating the microphone around the speaker, we build up this balloon of sort of energy versus angle. But you find that you need some phase compensation if you're doing array calculations. If the acoustic centre you measured, if the acoustic centre that you used for your balloon measurement doesn't actually match the geometric point of rotation. So if you're just doing one speaker, it's kind of, it is what it is, you measured it. But if you're starting to do calculations with arrays of these things, if the acoustic centre isn't where you think it is, and you start shifting them around and putting lots together in a mathematical model, then you start running into problems if this doesn't align. And that's led to something called the complex point source method, which seems to be the state of the art if you look in sort of software like Ease and things like that. So there's an extensive body of literature on that, notably by Feidstill and Arnett and co-workers related to Ease and that software. And what you find with this complex point source model is that you're no longer assuming directivity is omnidirectional, but you're still assuming that pressure decays inversely with distance like it would for a monopole. So when people say complex point source model, this is what they mean. So still decaying like a monopole, but actually got different energies in different directions. And that is something that's not strictly a solution of the wave equation, but if you're far enough away from the source, then it basically holds. It's a far field approximation. And that's one of the fundamental differences here. Van der Kooi is working in the near field. This approach was in the far field, this approach for ease and all that software. And in that kind of domain, you tend to find that the setting of the Acoustic Centre seems to be done quite empirically, where users are basically choosing it based on known transducer parameters. So you might guess that maybe the low frequency Acoustic Centre is where the low frequency speaker is, the high frequency Acoustic Centre might be where the horn is, the high frequency transducer. And if you were taking a guess at where the overall one was, then maybe it's in the middle, but who really knows? So this is kind of where people are up to for kind of full range loudspeakers. And I did use this image to sort of promote the talk. I must admit which was kind of because it was the nicest one in the slide stack, but it is slightly misleading because what I'm going to mostly think about is lower frequencies, where not so much this kind of multi-way loudspeaker, but systems where you might have a single way loudspeaker, but maybe it's like a cardioid subwoofer that has it's a single object playing a single signal, supposedly coming from a single position, but it's actually designed to not be omnidirectional. So the previous things that people have done won't work. So then there's this whole area which I've alluded to, which is relation of Acoustic Centre to spherical harmonics. So recently, holographic loudspeaker methods have developed that aim to not need an anechoic chamber. So Manuel Mellon and co-workers at Le Mans used pressure and pressure gradient. You can see they've got this little array of microphones here that measures the gradient of pressure, how it changes position, radially on a hemisphere, and they were using that to measure subwoofers without room reflections. Because you may or may not know, but even our anechoic chambers like ours aren't anechoic at subwoofer, sub-bass frequencies. It rolls off, stops being anechoic about 80 hertz or something like that. And then based sort of on that and extending it, there's also Klippel and Bellman published theory behind their near-field scanner product in 2016. So this aims to work in normal rooms. So this is a robot, but unlike the one that we've got that moves the speaker, this keeps the speaker stationary and then moves the microphone around the robot. And this is able to measure enclosing surfaces of the pressure field. And it's also able to do that at different radii as well, which then effectively lets you measure the pressure gradient like these guys were doing. Both based on a weighted sum of spherical harmonic functions, which I'll talk about a little bit more in a minute. Klippel and Bellman discussed the need to place the spherical harmonic expansion point near the Acoustic Centre. And this, to be honest, was sort of my starting point in maybe like 2021 or 2022, and I was sort of mulling this over before I kind of got into reading up in the literature. I thought, oh, that'd be a good idea. No one seems to have really looked at this. Maybe this could be my novel thing that I propose. That if people say the expansion point should be near the Acoustic Centre, then maybe the Acoustic Centre should be where the spherical harmonic series converges fastest. Then I kept reading the literature, and the other thing that you really read about is people look at Acoustic Centre for musical instrument directivity. And in that field of literature, they define the Acoustic Centre as the expansion point for where the series. So that idea seems to have been beaten to it. In that idea, that didn't work. But nonetheless, an interesting body of literature where people are looking at musical instrument directivity, often for things like virtual reality. If you want to put synthesized avatars, playing instruments into virtual reality simulations, you need to know the directivity of the instrument because it'll have a big effect. So Ben Hagai et al., Michael Verlander showed translation to a suboptimal expansion point means you end up using more, an unnecessarily number of high-order terms in this series to try and capture the directivity for the same accuracy. And if you're going to do that, you start needing a spatial search looking for where this series converges fastest, and you need the minimum amount of data to represent this thing. And that's really one of the differences compared to this stuff for omnidirectional sources, is as with Van der Koy's work, the two microphones each side of a speaker, you get this closed form simple expression that just tells you where the AC is, the Acoustic Centre is. With the other work that Bellows and Leishman have done more recently, you can do the same thing but in a bigger sort of theoretical framework. And there's a lot of advantages to that, to be honest with you. I mean, and they're saying that they see sort of searching numerically as a disadvantage. And I can see that. I mean, there's obviously computational time costs, and there's the possibility the Acoustic Centre is not found. So if you've got a closed form expression, that's great, but it doesn't seem that there's anything available for anything past omnidirectional sources. There's some scope for producing, therefore, different search metrics. As soon as you start searching, it's like, what are you searching for? Ben Haggai et al. Used one based on the coefficient values. Shabtai and Vorlander used one based on phase, and I've done one based on reconstruction error, which is something new that I've done. So on to the kind of methodology for this. Please do shout out questions if you have while I'm going along. I've done finite element method simulations in COMSOL multiphysics, so apologies to anyone who wants to see some real measurements. This is all simulated so far. This has then been post-processed in MATLAB via the COMSOL MATLAB Live link, which is a great way of getting data to and from COMSOL if you're ever working with this. I've been using axisymmetry as Van der Koy did in his simulations, and this is massively faster because it basically means you only have to simulate a radial slice. Instead of trying to simulate a whole speaker and the whole domain, you just do a slice of it in radius, which is far, far faster. So that might seem a little bit fake, but there are actual real applications of this. This is a picture from a paper by Charlie House and Jordan Cheer down in ISBR, where they were looking at acoustic cloaking of something that I don't think the military wants us to tell us what it is. They're using speakers here that, as you can see, they're little cylinders. They've got a speaker in each end, and they can be any combination of monopole and dipole. And as you can see, they're constructed axisymmetrically for simplicity. So there are actually some applications in noise control where you might actually want to do that. I was also motivated because I had this scheme for this kind of loudspeaker prototype where I had this cardioid bass stage, which is these two speakers in a tube that's aimed to kind of end fire. And the idea of this was it was intended for sound field rendering or control applications, like we just saw, where precision knowledge of source directivity is required. I've realised over the years I've been doing a lot of, sort of computer simulation work in acoustics is there's a big problem, even if the algorithm's okay, there's a big problem with what's the input data you're simulating. If you don't, it's all well and good knowing the geometry, but if you don't know what the materials are, or you don't know which way sound's going out the source, then your simulation is basically always going to be wrong, no matter how good your algorithm is. So I was kind of interested from that, turn that around, let's build a source with some very well-known directivity. And there's some advantages of making it axisymmetric. It turns out that it square roots the number of coefficients you need to encode the directivity if it's axisymmetric, and therefore it also square roots the computational cost of translation operations. What do I mean there? Well, if you're a listener, then you've kind of got a certain coordinate system. There you are sat, and you've got some perception of height and angle and things. The loudspeaker, on the other hand, wherever that is kind of its angle, and it's got its own set of coordinate systems around where it's based. So you will measure this speaker, probably in a lab in some orientation, and then you've got to, mathematically, when you do sound field rendering calculations, you've got to compensate for the fact that it's not there, it's over there pointing in some particular direction. And there's a translation. Yeah, so you've got to rotate it round to the right direction and translate it over. And the cost numerically of those operations square roots as well. And usually we'll see, from Van der Koy's papers and from other literature, you expect the Acoustic Centre at the low frequency stage at least to be in front of this front driver. And I had this kind of concept that maybe I'd put some sort of coaxial mid-high stage there, which led to this prototype speaker, which a couple of students have worked on, including Gabriel, who's online, I just saw a minute ago. which, as I was joking, is really also, so there's some serious motivation for this in terms of maths. There's also just actually wanting to saw up wood and build speakers, and as someone once said to me, and it's kind of stuck with me, you know, if you're going to build loudspeakers, don't just build speakers that are like the ones you can go and buy from a shop. Build weird loudspeakers that nobody's thought of. So here's my attempt at a weird loudspeaker. Right, so on to a little bit of theory. I've kept talking about these spherical harmonics and I've not actually said what they are yet. So spherical harmonics, mathematically, are a family of orthogonal functions defined over a sphere. I'll show some pictures in a minute to make that make sense. So they have an overall order n, so this would be kind of, are they a monopole, are they a dipole, are they a multipole, etc. And then there's some azimuthal order m as well, which basically says which orientation they're in. So I'm going to start off with an omnidirectional source here. So here's I've got a little coordinate system here where beta is my polar angle down from the sort of the top of this, the pole of this coordinate system at the top, and alpha is the rotation angle here. And I'm kind of assuming the speaker's in what's called front pole orientation, isn't when you're describing it, it's pointing up as far as this coordinate system, the way I've drawn it's concerned. So the zeroth order term is just an omnidirectional term, here indicated by red. Apologies to those in the room, this projector seems to not do colour. Yeah, so that's just the same energy in every direction. Then if you move to order n equals 1, then you start getting dipole terms, and these, again, you can have different orientations of these, so you might have vertical and then x and y, so you end up with 3 different ones, and they're indexed by the different m numbers. If you go to n equals 2, then you go to kind of multipole, higher order directivities, and now you get 5 of these, and yeah, and you start getting more different orientations. Now, if we say that this speaker's axisymmetric, as in everything's irrespective of alpha, this little sort of spinning coefficient going round, then you only end up needing to use the centre column of these, the m equals 0 ones. So you know all the others are going to be 0 because they're associated with non-axisymmetric behaviour, so you can ignore all of those. And you might notice here that if I'd gone down from order 1, then I'd gone down from 4 to 2 coefficients, which is a square root. For order n equals 2, I've gone down from 9 coefficients to 3, which is a square root. So that's where this square rooting statement comes from. These are really useful for interpolating any data over a sphere, any data at all. So if you Google spherical harmonics, you'll find them being used for all sorts of things. So they're excellent for, because they're orthogonal, they're excellent for interpolating data over a sphere. And this was Loudspeakers by Jamie Angus and Evans, that's the first name, in 1998. Jamie Angus, who's an emeritus professor here, I think he was at York. She was at York actually when she did this work, but she's an emeritus professor here now. I was in the room when I was last giving this presentation. And these look like this. So we've got a summation over the overall order n. So is that the kind of, is it a monopole, is it a dipole, is it a multipole kind of thing? And then it's n. Within that, we've got these ones with different orders, which are the different columns in that diagram I had a minute ago. So different dipole orientations and things. Now, of course, for axisymmetric, we'll find that we'll only use m equals 0. So actually, we won't use this second summation. And this is, if you're going to encode a pressure field at a particular radius, which is what people would normally do, then you find that this is the pressure at that radius, at this polar angle, at this azimuth angle, and then at this certain frequency here. And we use the spherical harmonic functions to encode the sort of variation over angle, such that we just have some coefficients of those, and they depend on frequency, because we're only going to encode data for one frequency at a time. They also depend on radius, because there's no consideration of radius here, so we can only encode for whatever radius is we're using. And because these are orthogonal, there's a statement here that lets you encode them, and I won't try and unpack all of this, but basically just to notice that this would be the pressure field you measured. These would be the spherical harmonic functions, and you can basically do an integral with them and get the coefficients directly. Now that might look vaguely overbearing, but actually this is quite good, because in practice what you're going to do is approximate this integral by data from the some measurement points. And what this essentially tells you is you can use the data from the measurement points pretty much directly if the measurement points are appropriately chosen. Whereas most other systems you'd have to do some sort of matrix solution to find some of these terms. So it means you can find them directly, which is really beneficial. Then we go on as this concept called spherical basis functions, and this basically throws something else into the mix. So we saw that spherical harmonic functions are really good at just interpolating over anything spherically, just over angle, over a sphere. But we know we're dealing with acoustic waves, so we can use that information as well. We can use the fact that these things have to satisfy the Helmholtz equation. And it turns out that if you know what the thing's doing in angle, because it's a spherical harmonic function of some particular order, then you can actually deduce from that what it has to be doing radially as well for this all to be a valid acoustic wave. And that means that if you knew the angular stuff, you automatically know the radial stuff as well, which is really, really useful. Same coordinate system. And just to point out here that the angles here, I've written R minus R naught. So I'm thinking of what is the position of a microphone relative to some expansion point, which is essentially the trial acoustic centre that I'm going to be looking for. In this expression here, I've written HN out, which is a spherical Hankel function. That's the outgoing type. You can have waves that would go out. You can also have waves that would converge to a sink. You can have waves that would come through and sort of pass through and go out again. So there's three types. There's outgoing from a source, incoming and passing through. And these are what the Klippel near-field scanner used to eliminate room reflections. It knows that if you've got a speaker, everything it's looking for is of the outgoing type because it's coming from the source, whereas anything coming back from the room has got to be coming in from the room, passing through and going out again. So it can separate the outgoing from the outgoing speaker sound from the room reflections. And that's essentially how it works. And a pressure field can be expressed as a weighted sum of these. So we've kind of got quite a similar looking expression to before, but now we've got this radial function thrown into the mix as well. And that means that the coefficients of this are independent of the radius you measure at. So this is really useful. You can measure any radius or extrapolate to any radius, and you've still got this same set of coefficients encoding what the source directivity is. However, they do depend on R naught, the expansion point, which is the trial acoustic centre. So, just to make some little comparisons here. So, if you kind of start with the spherical harmonic function expansion, I give this a smiley face because I don't know if you're all familiar with it, but certainly it's more well known in spherical basis functions. There it is. That's the equation I had in the previous slide. So these only interpolate over angle, so the coefficients are a function of radius. So if you measure coefficients at some particular radius, they're only valid at that radius. Spherical basis functions, given that a more scared face, because it's slightly more complicated. Basically what happens is we've thrown in this spherical Hankel function, so now these coefficients are valid at any radius. So they can be used to interpolate between radiuses. And if you compare these two things, you'll notice that actually they can be related because most of the two expressions are basically the same. So you can find the coefficients from spherical harmonic functions for the CMNs from the BMNs just by scaling, which means you can get from one to the other. So those two things you can get between. The other thing that people might think about is what you call the far field pressure, which is when you take the limit and you go away from the speaker and you kind of go away looking at how the pressure field's varying, but compensating for how you'd expect a monopole spreading to be. So that's what that is there. So you take the limit as you get far away, and what you essentially getting out of this is the far field directivity pattern without any of the spreading term in it. And you can also, that's just a pattern over angle. So you can also encode that with spherical harmonics. We don't need the radius here, because what we've done is we've said, oh, we're going really far away where the radius doesn't really matter anymore, and try to make something independent of radius. So we can use put those two things together and encode this far field pressure in this way. I've just called these coefficients D just to point out that they're different from C. And you can relate those, it turns out, back to B. So actually, if you know the spherical basis function things that hold at any angle, actually you can really easily get the far field version as well, which would normally be quite difficult, but you can do that very easily. Final thing on this slide is we have the complex point source model, which is very accepted and widely used in software. And if you compare those two statements, you might note that these are pretty much just the same thing written the other way around. One is saying, oh, the far field pressure is the limit of that. The other one's saying that, oh, actually the pressure of some radius is more or less equal to the far field times that. So actually the complex point source model just uses the far field approximation, which means these two are essentially the same thing. And because, as I just said here, this far field model we can find directly from these spherical basis functions, it's actually just, these two things are actually equivalent as well. So this one starts off looking like something quite unfamiliar and perhaps a little bit more formidable, but you actually find that if you go into the high frequency limit or the long distance limit, it's actually just an approximation of what everyone's using in industry already. It's just a version that stays correct as you get closer, while as the complex point source model falls over in the near field. So how might you measure these? So you can just measure pressure at some known radius. You'll then find the spherical harmonic coefficients directly by orthogonality, which was the integral I had before. And this is okay, but it requires measurement on a spherical surface. It requires anechoic conditions. And you can then find the coefficients for the spherical basis version from the spherical harmonic ones, like this microphone radius. That's okay, but it's all locked to the centre of the array, so you can't kind of change the virtual acoustic centre post hoc, if you like. It's locked to where you measured it. The other possibility is this method by Manuel Mellon I mentioned before, where you actually look at pressure and its gradient, and that does let you find the BNM coefficients directly. It still, however, requires measurement on a spherical surface, and it's the expansion point still locked to the microarray centre. I forgot, did I say this is supposed to also eliminate room reflections? I didn't write that. The Klippel measurement system, which is a commercial system, that actually finds the spherical basis coefficients by matrix inversion, which therefore means that actually it's an arbitrary measurement point cloud. We're not locked to spherical surfaces anymore. It can actually measure wherever it likes, and then it just keeps inverting things, which is kind of okay so long as the matrix inversion remains well conditioned. It only requires pressure. It just measures pressure at lots of radii. And it lets you choose the expansion point quite freely. So of those three, things are obviously much more customizable with this latter method. The method I've actually used here today, though, is a slightly different one, which is something I came up with in 2014, where you find the coefficients of these spherical basis functions directly by orthogonality. You can do it on any shaped surface, as we'll see later on. The expansion point can be chosen completely freely. And it uses a slightly odd quantity that I call cross intensity, which I'm not going to have time to talk about too much today. But suffice to say, you need to measure the pressure and the pressure gradients when you're measuring. And what you end up with here is you end up with stop working. You end up with the pressure you measured with the velocity of the wave you're looking for conjugated times the pressure of the wave you were looking for conjugated times the velocity you measured. So this is kind of like cross terms between the wave that you measured and what you're looking for, where what you're looking for would be one of these spherical basis functions. And you might have noticed, if you were looking really closely, that this is actually an intensity probe I had here. This is a microflow intensity probe, which has got one of these little hot wire anemometers in it that will measure particle velocity. There are other types of intensity probe around. This is what we had, which I was using. There's something new there as well. Right, so on to some stuff about the actual sense for some theoretical multipoles. So I said, back to my outline maybe. Yeah, so I said I was going to just look at some analytical sources. Oh, where's it gone? Here. So my process here is actually, I'm going to start off in terms of trying to benchmark and check my post-processing is working correctly. I'm going to start off with just a mathematical definition of a source directivity that I know. So I'm going to say something like, this is a dipole, or this is a monopole or multipole in a certain position. And that means I know the order, I know the true acoustic centre, I can propagate that out to some simulated measurement surface where I pick off a lot of kind of simulated pressure and pressure gradient measurements, as if I'd use that probe to go around and measure all of these. And then I imagine some trial acoustic centre to see that I'm going to expand onto these spherical basis functions with. And essentially what I'm going to do is just, oh, there's the expansion. Essentially what I'm going to do is I'm going to, so I know the ground truth, what was the proper acoustic centre, what were the coefficients, and then I'm going to compute them and see how they match. And basically what you'll see in the slides that follow is I'm going to move the trial acoustic centre around, only vertically here because everything's axisymmetric, and I'm going to look at whether these two things match, is essentially the metric. So we've basically been looking at plots of error. And this is, well, it's actually plots of, sorry, this is plots of coefficient magnitude, my apologies. So this is a monopole, and this graph is of the kind of translation distance, the difference between where the monopole really was, whereas where we're imagining it was when we tried to work out what its directivity is. And you can see that if you've got zero offsets, you get absolutely bang on, then you only need n equals 0 to explain all of the acoustic behaviour. Because it was a monopole, it only had n equals 0 behaviour. And all the other terms just sort of shoot off down to 0 and disappear. But if you actually get your expansion centre wrong, you're trying to expand a monopole here as if it was there, then what will happen is you'll start to get loads more higher order terms required to kind of compensate for the fact that your source isn't quite what you're saying it is, and compensate for the fact that it's, you know, it's all a bit out of phase and got different level and different directions. So that's what that is showing us, and we're kind of, you know, looking at this and thinking, could we search through these results to find the correct position? So there it is. If I did a dipole instead, so this is a dipole now, the graph looks very similar, but if you look carefully, the line that's at the top here is the orange one. So if you're right in the correct position, then you'll find the n equals 1. The dipole line explains all of the behaviour, and all the others bunk off to 0. But if you get your expansion point slightly in the wrong place, then you start needing other higher order terms to explain what it's doing, which in terms of trying to encode this data for, you know, virtual reality or something, it's just wasted data. It's just more data to represent the same source because you got the position wrong. Then we got a vertical multipole. So this is one where I've let the coefficients be 0 for up to n equals 2. And you can see here that all n equals 0 to 2 are required to get the right values up here and explain the behaviour. But again, if you're in the wrong place, you start seeing these other higher order terms basically coming in to express the fact that you've not got the source, you know, you're not expressing the source in the place that it really is. So you can see that this kind of concept of true acoustic centre and the sort of test acoustic centre will give you different coefficients in these series. And we're looking for the ones that give you the sparsest representation where you need the fewest coefficients. I've been sort of going, but for a real loudspeaker, we don't know the actual coefficients or the true acoustic centre. If we did, we wouldn't be measuring them. So that's kind of toy problem where I already knew the answer before I started. And to do this, we're going to need a metric we can evaluate to search. And the process that I'm going to follow is I've got a measured pressure field, which I call P_m for measured, its gradient, and encode that onto a set of coefficients based on the trial Acoustic Centre, which is the thing I'm moving around, seeing the effect of moving that. I'm then going to reconstruct the pressure field back to the measurement positions again for some given order of sort of assumed source order, monopole, dipole, multipole, etc. And we're going to compare the reconstructed pressure to what I measured to basically see whether they match or not. And that's the near field version. So if I'm just doing this at the measurement radius I already have, then I just do that directly. If I wanted to look at things in the far field, so it might be more useful for a speaker not to just measure it and understand it at the measurement the microphone happens to be in the anechoic chamber, but to do it as if you're really far away at a concert or something. So we do a far field version where we extrapolate the near field data out to the far field. We extrapolate the encoded coefficients into the far field, like I showed on the slide before, and then we do the same kind of comparison, but on pressure really long way away. So there's a far field version as well. So this exists in near field and far field versions, and the reconstruction there is just a normalised RMS of the residual. So what is the difference between these two things, the measured and the reconstructed, normalised to the RMS of the measured. So that's what we will see on the next slide. So this is a residual. So this is a vertical dipole at z equals 0.2. So the correct AC is there on these graphs. So you can kind of, so this is that I've just highlighted that z equals 0.2, and I've just highlighted it for the n equals 1, the orange line. Apologies again for the projector colour on the projector for those in the room, and the place where that dips is essentially where we're imagining the Acoustic Centre will be, because it's explaining all of the error. There's no more. You don't, with this, what this graph is telling you is at this location, you don't get any better by trying to throw higher order directivity into the mix. Saying it's a dipole has explained everything that's going on. And this top one I say is the one measured in the near field. This one is the far field extrapolated version at the bottom. And we can see here that on the near field one, you kind of get this sort of valley that gets wider but not any lower. So if you start throwing more and more higher order terms at it, then you can still get good accuracy. That's about sort of 2% accuracy there, but over a wider range of Acoustic Centre positions. But you get the most sparse encoding with just the dipole term when you get the Acoustic Centre right. In the far field version, things are a bit different. What happens is you start kind of overfitting really. So the error keeps getting lower and lower because I don't know what we're overfitting, but we're overfitting something or other. So this is not really so useful. So this one, if we were searching around to try and find, if we didn't know the source order yet, then this would be quite a useful thing to search with, because we can look for the minimum error, we can look for the thing that gives the narrowest notch, and we can probably work out both where the Acoustic Centre is and what the order of the source that we're dealing with is. So that's what I've used mostly in the paper. But later on I also used this far field one because I was optimising a cardioid loudspeaker at a significant distance. So I'm going to skip something there. Just watching the time here. So let's have a look at this for a single axisymmetric speaker. So what I've got here is I've just got a single driver in the front of a cabinet. I've got an optional obstruction that I might throw in there, which is, again, think about from the start of this presentation, thinking I might put a mid-high driver in front of the bass driver. This is just something I can put in or take out to show the effect of putting this lump in front of the driver. And yeah, this is 260mm diameter, 300mm deep, centre with its baffle at z equals 0. We've got a PML, perfectly matched layer of PML around this to stop reflections around the FEM domain. And then just a prescribed velocity condition on the boundary. So I'm not looking at the effect of the radiation impedance or any of the kind of electroacoustic circuitry in the speaker here. It's just being told I'm moving like this. So I've got this optional ability to drop this kind of obstacle in front. And for the encoding, for the spherical harmonic encoding, searching for the acoustic centre, I'm extracting data at 0.9 metre radius. And I'm using the same process as I was for theoretical multipoles, but I'm trying to find the acoustic centre for something that's a bit more realistic. And what I'm doing here is I'm actually searching around through the kind of pictures, the search spaces that we had before, and I'm basically using an MATLAB's fmin search to try and find the acoustic centre that gives me the minimum error. And what we see is we get graphs a bit like this. So just concentrate on the bold lines for a minute here. You can see that the omnidirectional acoustic centre starts probably about kind of, I don't know, what is that, about 9 centimetres in front of the driver. So it's in front of the driver, which is what people normally expect. Then it kind of gets a little bit further away, and then it sort of drops back back towards the cone as you get higher in frequency. And you can see the error associated with that is quite stable, and it's then increasing and increasing. So what this curve with the error metric at the bottom is telling us is that, you know, at kind of 10 to 100 hertz, we're explaining almost all the behaviour with just a monopole behaviour. But as you go up in frequency, there's more and more things happening that you're not explaining. And that's these other terms coming in from the bottom. These are the higher order terms, the dipole term, the second order term, etc. And I've just shown where the location of those two is on this top graph. So if we're looking for the acoustic centre, if it was a source that actually was allowed dipole behaviour as well, then that comes in, and it comes in a different position, which is quite interesting. So unlike for the theoretical multipoles where you said, oh, actually I'll allow this thing to have a higher order directivity, and you still get the same position come out, with the speakers, what you actually start to find is that as you allow the model to fit more accurately with higher order terms, you actually lock onto different positions. It's not actually completely unique, which is something that I didn't expect, and something that's not really written about enormously in the literature. So what we can see, then the dashed lines are for the effect of putting this obstruction in, which is this other thing I was interested in, you know, what happens when we put this treble stage in the way. And you can see that the obstruction actually shifts the acoustic centre back by about 1.39 centimetres. And you can see this here, that there's comparing the two at 400 hertz. If you were to go up to something like a kilohertz, then you actually see some rather more dramatic differences. And we've got the acoustic centres just overlaid on there in orange and blue and orange. Trevor's going to make an exit. Nice to see you. And you can follow this through an animation. If you go up in frequency, might be, sorry, apologies to those in the room, again the projector's not very good, but you can see the acoustic centres moving around, and the higher order ones appearing, explaining some of the different behaviour. Okay. What about optimisation of cardioid loudspeaker? So this is just trying to draw this round to. I'm going to skip in a bit on the baffles because obviously not got enough time. So this is back to my prototype speaker here. I'm going to ignore the front bit and just look at the two woofers in a tube. So the idea is how cardioid can we make this thing? And this had two 210mm diameter woofers in it. They share a common chamber to exploit the efficiency gains this gets, which was shown by Jordan Cheer in 2015. The rear plate and things really for practicality of mounting. You can see it's kind of bolted on the robot over here, and discourage backward radiation from the rear driver at higher frequencies. And they're fed by separate amplifier channels, meaning any combination of monopole or dipole can in theory be achieved. What we're trying to do is get cardioid behaviour. So essentially what I'm doing is I'm saying I need to optimise a front to back filter that says how is the amplitude and phase of the back speaker related to what the front one's playing. I've got a more sophisticated model for this, which was actually worked on as part of the student MSc project, and very similar, but sort of double in length and 2 loudspeakers. The loudspeakers themselves also have simulated circuits that implement their lump parameter model of electroacoustic behaviour, so their internal damping. It also it uses the feel small values of the drivers and the physical prototype, and it also means that both cones can move when only one driver is driven. This does happen quite significantly in the actual prototype, that you drive one speaker, and because the other one's just at the end of a pipe in the same air cavity, it will move as well. And that's quite a big effect on the directivity you get. The internal air volume of the cabinets as modelled, the majority of this is filled with wadding material, which was modelled with a Delaney and Basley model. Okay, so similar kind of process, but a little bit more complicated speaker. And what's quite convenient is that because everything's linear in this model, I don't have to sit there in COMSOL trying to put the filter in COMSOL. I can just simulate the front behaviour and the back behaviour separately and then combine them afterwards. So I can do a simulation as if just the front speaker was driven, then I can do a simulation just as the back speaker was driven, and then I can basically apply a filter in MATLAB and then sum the results together to get what the total speaker would give, which you can see here most of the radiations going forwards. And we can use this, actually, it turns out, to solve for what the filter should be. This was something that an undergraduate project looked at last year. And but what we find is that the resulting residual, the error that you get, how not cardioid it is, actually depends on the acoustic centre that you choose. So you end up searching for an acoustic centre that minimises the residual. I'm going to skip a slide with a load of equations on, go straight to the results. So this is the acoustic centre for each of the drivers driven separately. So the solid lines are the front driver in the chamber, the dashed lines are the back driver in the chamber, and the grey area, which you unfortunately can't see on the projector, which goes from about there to there, from about minus 0.4 to plus 0.2 is where the actual physical speaker is. And if you measure this, you can see that generally the front omni term, so this line here, is more or less in front of the a bit in front of the speaker, at least at high frequencies. There's probably a bit of something going on here to do with the top and bottom speakers coupling, and that's pulling the acoustic centre back as the driver gets activated. But you can kind of track this quite nicely. You can also see that the rear omni acoustic centre is again rather close to the baffle due to this plate. The other thing that shows up in the data, if you look at the error metrics, you can see that at the very, very lowest frequencies, the omnidirectional behaviour explains almost everything that's happening. But as you go down, hang on, no, sorry, tell a lie. Sorry, it's right around there. Sorry, if you just use the omnidirectional term, you actually get very significant error. You know, if you assume this is omnidirectional at the lowest frequencies, you'll find you get about 80% error. You really have to have the dipole term in right from the very, very lowest frequencies. I think that's because the two drivers are moving in sympathy with one another in the tube. Later on, as you go up, you come to a point here around about sort of 200 hertz, where the dipole term actually is less significant. So actually, this speaker starts off being very dipole at the lowest frequencies, and then as you turn the frequency up, it actually becomes more monopole for a bit, which is very unusual, and then goes off and becomes higher order afterwards. So that's quite unusual. And you can do a filter fit on this, so you can filter for what is the optimal relationship between the front and back. This is the real and imaginary part of that filter here, which I don't expect to see much of, except we can see the result of this is that when we work out the acoustic centre afterwards, we find that the Omni one is kind of within the this is the acoustic centre of the dipole. We can see it's pretty much in the middle of the cabinet, and we can see that the error starts very low and then gets gradually higher. So what kind of happens is it all works pretty well up until about 350 hertz, and then you can tell from these sort of jagged lines stuff starts to go wrong. So the optimization's worked quite well. It's made the speaker very cardioid, up to about 350 hertz, which was okay because that was when I was intending on switching into this coaxial mid-high anyway. So there's the low frequency. Is this going to work? Oh, I was thinking about it. Yeah, so you can kind of see the three simulations there. So the one on the middle is the only driving the. Oh, those two must be the wrong way around, actually. Are they? Yeah, those two. I think those two simulations are the wrong way around, actually. This must be driving the front speaker. That's driving the back speaker only. And this one on the left-hand side is the combination of the two, which is the actual behaviour of the whole thing. And you can see we've just got this, whereas these ones have their acoustic centre obviously near the speaker, when you drive the two together, we've got a clear dipole behaviour sat fairly central to the whole thing. And if we look at the polar plots of that versus angle, so again, the colours unfortunately on the projector are pretty awful, but the front and the rear drive, when you drive them on their own, basically look omni almost all the way through the frequency range, whereas if you get the two of them working together, then up into about 300 hertz, you can pretty much achieve cardioid behaviour. So you're throwing all the sound forwards with about a kind of 40 dB front to back ratio, more or less. Right, so just to wrap up, a directional low frequency acoustic centre concept's been proposed and demonstrated with 3 simulated test case studies. The metrics can be used in a search that identifies the acoustic centre for different orders and frequencies. It was used to optimise a cardioid loudspeaker directly, and this, importantly, wouldn't have been possible with the previous work where you assume that the speaker has to be omnidirectional. If all your acoustic centre concepts require the source to be omnidirectional, you can't optimise a cardioid loudspeaker because it has dipole terms. So further work is to apply this to non-axisymmetric models and some measured data, which I do have but haven't quite got through yet. Find a process to detect the order of a source as well as the acoustic centre. I've actually got some other material on that, which is not in the paper, and I did have some in the slide stack, but I skipped it due to time. This is often quite challenging because you actually, as we saw, the acoustic centre actually varies with what reconstruction order you're trying to do, and the search space isn't convex, as you call it. It can have multiple minima, so you can actually find the source has more than one possible acoustic centre, which can be quite difficult. And then the other aim is to try and achieve some synergy with high frequency acoustic centre concepts like the stuff for the loudspeaker measurements of the horns and things. So thanks to all the students who've done dissertation projects related to this. Thought I'd just name them here since a lot of them are Salford students. So Paul Vedier, now at Apple, worked on the dual loudspeaker COMSOL model. Alex Booth, you told me where you were the other day, I've just forgotten where you're now working. Worked on the cardioid optimization process last year. Mahmoud Masri, now at Meridian, studied the spherical harmonic near field to far field transforms. And Sean Nielsen, now at Resonado. Gabriel Whittle, doing a PhD here and online. Dario Nicolai, must confess, I don't know, I keep hearing from him, but I don't know where he actually is right now. All took projects related in some way to the speaker concept or some of the measurement related stuff. And thanks to David and Jack at KEF for providing the loudspeaker drivers in my hobby woodwork project. Right, thank you very much. And yeah, thank you for listening. Any questions? I've managed to fill the whole hour.
Any questions in the room? Or online?
I got a question for you, John.
Well, I've muted everyone. Try again. You talking?
I was talking. I had a question for you. You kind of answered it though. So I was just thinking, how do you know when you've got to kind of the optimum? But I guess you're kind of saying that in your conclusions, it's quite difficult. I was wondering what the aerospace looked like. Is it, is it quite lumpy?
If only I had that on a slide. The aerospace, certainly for these theoretical poles, looks Well, I've got it for theoretical monopoles. Oh, I have got that as well, actually. So for the theoretical monopoles, it ends up looking a bit like the bow of a ship. If you kind of plotted this with the different spherical harmonic orders, you can kind of, and then the error vertically and the trial AC the other way, you get this sort of shape a bit like the bow of a ship, and you can kind of be searching and looking for that, which is kind of something that's possible to find if you just have some sort of penalty that penalises higher order spherical harmonic order, like you sort of tilt the surface. You'd find that quite easily. It sort of works for the monopole as well, works okay for the higher order multipole. They're quite easy, and I think when I first started this, that's one of the things that made me think this wasn't going to be so hard. Was if I actually go for this speaker, this one here, even this sort of simple speaker, just with this, even ignoring the obstacle and just doing a more realistic cabinet, you see a search space that looks more like this, where you actually get in multiple minima. So you can see there's multiple minima versus Acoustic Centre here, and the sort of loci of what gives you minimum error is not really so clear, and it varies quite dramatically with frequency as well. So we've still got this sort of bow of a ship sort of shaped thing, but there's some other minima here that you can get stuck in if you're not careful. So I was using quite a lot of random restarts to avoid that sort of thing.
Oh, okay. Yeah, because like the simplex algorithm, I think it uses, doesn't it? You if you're not careful, you're going to get stuck in a little ditch.
Absolutely. So I think that's one of the real problems. And I mean, conceptually, it's quite interesting actually. You watch this animation because you actually see that when the sort of dipole, you can probably see it better online than they can in the room, unfortunately. When the higher order terms appear, it sort of comes at the same time as sort of rear cabinet diffraction starting to appear. So I think at the very lowest frequencies, the omni term explains almost everything, and it's almost like you pick, past a certain frequency, you pick up a secondary source from the cabinet rear diffraction, and that's actually what's pulling some of this behaviour backwards. If you can kind of imagine that these kind of, I might just be imagining it because these wavefronts sort of happen to get to arrive at the cabinet just at that time in this animation, but that's kind of what I'm picturing. Oops. Thanks, Paul. Any other questions?
We had a question on the chat from Josh Meggett, who I'm not sure if he's still here, but what's the question anyway, which is, could you extend the methods to identify the acoustic centre of multiple distinct sources?
I think you probably could. The thing I missed out was the thing I skipped, which also isn't in the paper, but hopefully I'll get around to publishing at some point, was looking at sources over a ground plane, in which case you have to do a source and the image of the source at the same time, which is adds to the complexity of stuff. I mean, they're a bit different because they're not distinct sources. They are sources that are completely coherent because it's just a copy of the same thing. Whereas you're asking about multiple sources. I mean, what you're kind of heading towards then is something that's almost like an equivalent source method, which is when you try and express the scattering of something versus a number of sources with different positions and amplitudes and phases. Then people would normally use them as monopoles, but there would be nothing to stop them being higher order ones, in which case you might be able to use quite a lot of the processing I've done here for that. The other question is the fact that they're distinct is something that he said there, and that's something else a little bit different, because then you start having to think about what are the cross correlations between sources, are they coherent or not? And I've had other things on that, work on that as well. In fact, actually just looking at a paper related to that, some work related to that quite recently, where people had used a principal component analysis to try and separate out different sources in different locations on the assumption that they're incoherent with one another. And I've got a few areas of interest in that related to the satellite testing stuff as well, actually. So, thank you. Yes, don't know yet, but potentially.
All right. I think that's it for today. Thank you again, John.
Thank you. Thanks for your. Thank you all for coming.